This is the fourth in the Physics C videos about energy and work. And we're going to be talking about potential energy and conservative versus non-conservative forces in this one. This is going to be mostly new material instead of a review from last year. And it's where the distinction between a particle and a system becomes crucial. Because potential energy is an energy associated with the configuration of a system. You always have to have multiple particles to have potential energy. There are two important kinds of potential energy at this point. We'll learn more of them. This is gravitational and elastic potential energy. There are others as well. Electric is the big one. Now, in general, delta U is the change in potential energy. U is generally the symbol we'll use for that. That derives from German. It's complicated. And it's equal to the negative of the work done by some force. So this W is the work done by an internal force. And that's why we need the system. Potential energy is associated with a force that is part of the system or internal to the system. So for instance, if you're talking about gravitational potential energy, you must include the gravitational field in your system. And if you're talking about elastic potential energy, you must include both ends of the spring in your system. And essentially what this force does is that in doing work, it causes a change in energy from kinetic to potential or vice versa. If the force is doing negative work, what it's doing is it's taking kinetic energy away and turning it into potential energy. So that's if work is, positive. And if the work done by the force is negative, it's taking potential energy and it's turning it into kinetic energy. But the thing is, not all forces have potential energies associated with them. First off, of course, the force has to be internal to the system, but only some forces are conservative, meaning it has associated potential energy. So let's say that you change something about a system. You move one particle of the system farther away from the other one. It takes a force to do that, and that force does work W1. And then, so the two particles are close together. After the force does work W1, they're far apart. And then they move closer together. So the work to go from here to here is W1. The work to go back to the initial configuration is W2. Now, if W1 is equal to negative W2, so in other words, the total work is 0, then the particles would have the same kinetic energy that it started with, and you'd say the force is conservative, because it conserved energy. There's the same amount of kinetic energy after this as there was before. Now, if, on the other hand, W1 is not equal to W2, or negative W2, so the total work is some number other than 0, then we would say that this force is not conservative. And it's only conservative forces that have an associated potential energy. And right now, the important conservative force we know about is gravity. Springs are also usually taken to be conservative. The electric force is conservative as well. Friction is not, and we'll see why on the next slide. So gravity is a conservative force. Let's say you've got your system is the gravitational field and some weight. So we have our field and we've got a little mass m here. What we're going to do is we're going to move that mass m upwards a certain distance, d. And so the work done by gravity in that first motion is equal to negative mgd. It does negative work here. And now we're going to move it back to its starting point. So W2 in this case is equal to positive mgd, which is equal to negative of W1, and gravity is conservative. Now friction, on the other hand. Let's say you have a box on a tabletop. So our system is a box and a tabletop. If we start with the box here and we push it over here, and I'll make that. So W1 is equal to the force of friction times the displacement d, and it's negative because the force of friction is going to oppose the sliding of the box. Then we're going to move the box back to where it started. And we ask, how much work does friction do there? Well, on the reverse motion, the box is sliding to the left, and friction is therefore going to point to the right. And so the work done by friction will again be negative. So we say that W1 is not equal to W2, and so friction is not conservative. Now there are some other definitions of conservative and non-conservative forces that you need to know, and you should be aware that they're all equivalent. This one is very close to what we just said. If a particle travels along a closed path, which means it returns to where it started, the work done on it by a conservative force is 0. If you look at our examples here, gravity, the conservative force, W1 plus W2 is 0, whereas the total work W1 plus W2 done by friction is negative. So that's equivalent. Another definition is that the work done by a conservative force as a particle moves between 2 points does not depend on the path taken. And you can see that that is equivalent to that first definition as well. Let's say you have some closed path, like that, and you pick some point on the path, and you call those the initial and final points. Now imagine that we reverse the motion of the particle along those two paths. The work done as we move along the particle along this path is W1. The work done as we move the particle along that path is W2. Well, if it's a conservative force, W1 equals W2. And if we were to turn W2 around, it would become negative. And W1 would equal negative W2, which is what we said in our original definition. This path independence is the most useful definition of a conservative force. Now down here, these two things are not definitions. They're just facts about conservative forces. So if you're asked to give a definition of a conservative force, don't write these two down, but they're very important. If you have a conservative force, you know that it will depend only on a particle's position. The converse is not true, but if the force is conservative, it depends only on the position, and that means that if you have any force that depends on velocity, like say air resistance, it will be a non-conservative force. And last slide. In this example, you've got a roller coaster that looks like so. We want to find the work done by gravity as the coaster moves between the two endpoints. And let's say that the roller coaster has a mass of 1,200 kilograms when everyone's in it. Now, the really nice thing about a conservative force like gravity is that the work depends only on the endpoints. It does not depend on the path. So if we have this convoluted path, we don't need to calculate the work done in every little bit of it and then add those up in an integral. All we need to do is say that initially we start out at a height of 25 meters, and at the end we end up at a height of 6 meters. So the work done by gravity here is just mass, 1,200 kilograms, times gravitational field, times the difference between the initial and final heights. Because the coaster is moving downward, gravity is doing positive work on it. So we have 1,200 times 9.8 times 19. And we find that gravity has done 223 kilojoules of work on this coaster. So you should know the definition of conservative forces. You should be able to identify which forces are conservative and which are not. And you really need to know that path independence thing. For tomorrow, I'm going to check question 1 in chapter 8. And next time we will talk more about potential energy.